some new symbols like this meaning magnitude and knowing what magnitude means. The arrows on the end being a way to describe component form instead of parentheses, because parentheses would mean point, something different. Okay. But there's a couple formulas you could use to find component form and distance formula. Always a good idea to sketch the vector though. A visual helps you see, and a visual definitely helps emphasize that this is the horizontal component, this is the vertical component, and a good visual means you can count it and not have to rely on the formula. It's not always going to be possible, sometimes we do need to subtract this. But because this is positive 4, that's a way to describe that it's going right 4, and if this is positive 6, that's how we describe that it's going up 6. If these have both been negative, you'd be going left 4 and down 6. If for some reason you thought you were starting at Q and going to P, you would think those were negative, and that would be wrong. That's a common mistake. Alright, and since magnitude is just like the length of this vector, you could find the distance between the 2 points, which is where this formula came from, basically the distance formula. The distance formula is a variation of Pythagorean theorem, so you should see that you have the right triangle, whether you use Pythagorean theorem to get the square root of 52, or the distance formula to get the square root of 52. I guess we reduce that. 2 square root of 13, and you get the same thing. So, I'm showing you this, but 99% of the time I'm going to talk about this. I'm going to see the right triangle. Okay, so then you practice the same thing. You sketch the picture with left 10 down 7, so there's this component form. It's a vector, so we've got arrows. Pythagorean theorem could get us the length of the vector, which is the length of the hypotenuse, and Pythagorean theorem did that square root of 147. Questions about that? Remember that from last time? Alright, like I said, they would need to do some arithmetic operations, so some basic arithmetic. 2 times v means you double v, both parts of v. v minus w, or w minus v would mean you would take the horizontal component of w, subtract the horizontal component of v. Take the vertical component of w, subtract the vertical component of v. So, pretty much what most people expect. Dividing by half means you divide both parts by half, and if something has more than one step, 2w plus v, I suggest you find 2w, plus v, and then add them together. Probably not do that in one step. Alright, the rest of what we talked about was, so we used this for other stuff. We talked about what a unit vector was, and we started to see how that might be helpful. So a unit vector ends up being a vector in the same direction as the original vector, but with a unit of 1, a magnitude of 1. So just like unit circle has a radius of 1, unit vector has a magnitude of 1. It's unit singular. And one of the things you will certainly be asked to do, if you scan that worksheet, I'm sure you can quickly find a question or two where it says find the unit vector. You will make sure that that's one of the things that you can do. So, to find a unit vector, you need to know the magnitude of the current vector, which is why we practice some of that on the front page. And notice this one doesn't have points, it just has the component form. So I don't know where this vector is as far as graphing it, but it doesn't matter, because I have a visual. It goes left 3 and up 4. So you can find the magnitude, and so if it had a length of 5, it means we can divide that vector by 5, and then if it had a length of 1. Dividing a vector by 5 just means you divide both parts by 5. And the nice thing about that is it doesn't change the direction. It's still in the same direction, but now this has a length of 1 instead of a length of 5. So it's not hard to do, but just have to know that step. So sometimes we go one more step with it, and we say, alright, if I can change this to its unit vector, it's this guy, and it has a length of 1, then if I wanted to have a length of 1,000, I multiply by 1,000. If I wanted to have a magnitude of pi, I multiply by pi. This particular question wanted a magnitude of 7, so we multiplied by 7. So by manipulating the vector into having a length of 1, then we can multiply it by whatever we need it to get it to whatever magnitude we want. Changing it to a unit vector first is the key. So we practiced one of these together last time. Hopefully I asked you to try something. Here's a picture. Here's its magnitude. So dividing the vector by its magnitude gives me the unit vector. I rationalize to make it look nicer. So this vector is in the same direction as this vector, except this vector has this length, and this vector has a length of 1. And so if the question then said to make it have a length of 12, we just take the unit vector and multiply it by 12. So I multiplied it by 12 on the die. So that should at least convince you partly why unit vectors are nice. It makes it easy to change address. Okay, so let's practice that one more time. So I said that quickly. Let's practice it a little bit slower to make sure that you have that slowed down, and then we can move forward with some actual new stuff. Alright, so this vector is going left 3, then 9. So I guess you don't have to have a sketch, but I also don't know why you wouldn't make a sketch. Left 3, then 9. So you have your arrow to indicate direction there. And I want to find a vector in the same direction that has a magnitude of 5. So you need to understand that your first hurdle to that is to find a vector in the same direction that has a magnitude of 1. So then we're going to get that by taking this, call this vector v. If I took vector v and divided it by its magnitude, that would be its unit vector. But that implies that I know what its magnitude is. It implies that I can find magnitude. But with my picture here, it's a little more obvious. Just diagram theorem. So length squared plus length squared equals hypotenuse squared. So squared of 90. And you do want to make a habit out of reducing. 3 squared of 50. If you don't reduce your radical when you can, you're not going to get your answers also. Okay, so I divide this by 3 square roots of 10. That means both parts get divided by 3 square roots of 10. So those could cancel, and I want it rationalized. By the top and the bottom by the square root of 10. And then these could reduce. And I would like to rationalize it. So multiply the top and the bottom by the square root of 10. And then here's what you get. So it's a little messier. It looks a little more difficult than it is. Having magnitude, dividing theorem, dividing a vector by a number just means you divide both by 12. And you just happen to be radical, so you need to rationalize. Okay, so there's the first rule. I found a vector in the same direction as this one that has a magnitude of 1. So this is when the magnitude equals 1. But now, I can fix this so it has a magnitude of whatever. I don't even need to worry about this until right now. If I wanted to have a magnitude of 5, I should probably use different letters here. I'm just going to take the unit vector multiply by 5, which means you multiply both parts by 5. Here you're using the arrows on the end, not indices. And since this guy reduces, we would expect it to reduce. So there's a process to change it to a length of 1, and then there's a process to change that from length of 1 to whatever. You need to know both. So finish copying that down and see if you can formulate a question that you can. Okay, are you okay with the process? So, the unit vectors are good for these type of questions, but you will also just be asked to find unit vectors, as you can see from the worksheet. And then look like there's many other questions other than what I have heard of the sake way. So let's look at some other stuff. This we did not talk about. So you can write a component form of a vector like this, and my understanding is that mathematics likes to write it like this more, and in physics they like to write it a different way more. But you need to be able to switch back and forth. You will also switch back and forth on the quiz, the test, and in your book 7. So instead of saying the horizontal component is -5, you can say -5i. I is like the horizontal component. And instead of saying 3 is the vertical component, you can say 3j. But those mean the same things, just different ways to write them. You can write them with i's and j's, or you can write them with the arrow notation. So 3 -4 would be 3i, it's positive 3, so positive 3i. -4 would be minus 4j. This is negative, we want that to be. Okay, so sometimes you switch this way, and of course you can switch back. 5i plus 4j means 5, 4 with the arrows. And I minus 3j, okay, so that means the vertical component is -3. What does that mean, the horizontal component? There's 1j. So from here on out, it's going to be some questions look like this and more like this. But same thing. And when you're asked, I don't know, like if you really don't like the way this looks, at the beginning of the question, you could just make it look like that. You just switch it over if you want to. I don't think it's going to give you too much history. Okay, so we have component form, and we have something called trigonometric form. And each one has their own benefits, and each one can solve certain type of questions easier than the other. So sometimes we prefer one over the other, and you will need to be able to switch back and forth between those. Okay, so when I have component form, let's say I have number A and number B. So just generic A, generic B. What I like about this component form, we haven't talked about Precal, but what I like about this is I can quickly see how much left or right the vector travels. And from this, I can quickly see how much the vector goes up or down. So just eyeballing those numbers, I'm having a pretty good idea of the direction it's heading and that angle. But I know which way it's pointing and basically what weakness, and I can sketch it relatively easy. So how much it's moving horizontally, so just to get home at this point, if we use this vector, this is a horizontal displacement. It's going left 5, and then this represents the vertical displacement. Since it's positive, it would be up 9. Horizontal component's negative, it goes left. If the horizontal component's positive, it goes right. Vertical, positive goes up, negative goes down. Okay, so what would the horizontal displacement of this one be? Okay. And the vertical. So notice it takes you almost no time at all to answer that type of question. So that is the benefit of component form. That's one reason why we like to use that. Alright, the benefits of trig form, which I'm not showing you what that is yet, but this is what trig form looks like. You can quickly see the magnitude and you should quickly see the directional So I'm looking at our examples yet. I just put generic numbers in here. Let's say I said vector B was A, so some generic number A here, times the cosine of some angle on angle theta plus I sine, this has to be the same angle, J. When you look at it like this, the magnitude is going to be sitting right there. Right? And the angle that the vector would head towards, the directional angle, is going to be those two. And these will always be the same. So it's not that you can't figure those things out of that component form. It's just that they take some work. When we figured out the magnitude of those questions on the first page, we pretty much wanted to make a sketch and use the diagram here. So it's not that big of a deal. But if this is in trigonometric form, what do you think the magnitude is going to be? This one. It's sitting right there. So that's even easier. And what angle do you think is going to be that? That would be from the positive x-axis. Okay, so again, it's written in this form. You should instantly know the magnitude because it's sitting right there, and you should instantly know the angle that it's heading in the positive x-axis, like you did triangle questions. So they're just different. We do need to be able to switch back and forth. Sometimes we have component form, and we try to work with it in trig form, trigonometric form, and maybe we have something in trigonometric form, and we'd like to switch them. But they're the same thing, just different appearances. So that's what we're going to look at with the rest of this page. So we're going to talk about how to switch back and forth between those two forms. Okay, so 33. Now that we know the benefits of each, switch back and forth between them, find the component form of V, given the magnitude of 5, and the angle it makes with the positive x-axis of 30. Alright, since we have the directional angle, 30, and we have the magnitude, we have the two things we need for trigonometric form. So even though the answer is not supposed to be in trigonometric form, it makes sense to start in trigonometric form. So I will call this vector V, and magnitude goes out front, and the cosine of this angle in the y direction plus sine of that angle in the j direction. Now those are parentheses because I'm trying to indicate that this y is going to be distributed. Alright, so if the question said put it in trig form, it'd be correct. That is the trig form. I gave you the two things that you do and plug them in. But if you want it in component form, you would want to first distribute your 5. So 5 cosine of 30i plus 5 sine of 30j. Now, if that's a weird angle, I could approximate it with a calculator. But without a calculator, it might be done, unless it's an angle that we should know. Do we know much about 30 degrees? Supposed to. What's the cosine of 30? Okay, so 5 squared root of 3 over 2 in the y direction. Okay, do we know the sine of 30? Okay, so 5 times 1/2 in the j direction. So there's your component form. So in terms of I and j, if you'd rather have the arrow notation, then you could put a fractional. distribute step 5, evaluate it if you can, it's an angle we know, and then you can leave it like this or you can write it like this. Okay, I want you to practice that, but I want you to try to stay one step ahead of me. Okay, so I'm giving you magnitude and a directional angle, so try to write out what you think the trig form would be. What would the trigonometric form look like? So that's about 5 times more time than you should need, but you just saw this one in the first one. Magnitude, front, it's going to be distributed to cosine of the directional angle in the phi direction plus sine of 45 in the j direction. Now, the connection I want you to make before you try the next part. So remember when we talked about the unit circle and cosine has to do with the x values, horizontal distance, and sine has to do with the y values, the y distance? Well, look at how this is setting up. The cosine of that angle helps us determine the horizontal component left to right, and the sine of that angle helps us determine the vertical component, how much up or down. So it's still consistent with all of that. Okay, so that's what your trigonometric form looks like. So next, we need to distribute that 8, and you should know the cosine of 45 and sine of 45. So go ahead and fill that in, see what you get. So that would be a good start. Distribute. Since you're supposed to know the sine and cosine of 45, the only trig thing you really need, unless you count figuring here, you should simplify this a bit. This would be 8 times the square root of 2 over 2 for your horizontal component. Or yeah, let's just reduce those. This would be 8 times the square root of 2 over 2. Vertical component, and those reduce as well. So if you want to leave your answer as 4 square root of 2i plus 4 square root of 2j, that's fine. But also know that you can use the arrow notation as well. So why are these numbers the same? Did we do something wrong, or does that make sense with this question? If you're going 45, then just as much of your distance is going to the right as your distance is going up, right? But going to the right and going up at the same speed. So 45, that makes sense. So now what happens if we try to go the other direction? Well, it's going to look a little bit different. What if we wanted to be in trigonometric form, but we start off with component form? Something like 2, 3. So one thing we can do with component form quickly is we can sketch a picture. This one would be going right to 3. Easy to visualize. Okay, just like how we started the trigonometric form on the other page, we needed 2 things. We needed to know the magnitude, and we needed to know the directional angle. So if those are the two things you need to plug in, those are the two things you have to seek out. You're not just being told to this. But finding the magnitude is like what we did on the first page. Let's see, I have the right triangle. So I can think of this as Pythagorean theorem. That's one of the two things I need for trigonometric form. And I need to know the angle it makes with the positive x-axis. So how can I figure out that angle? Log cosines, you would need to know three sides. Log sines. Okay, well first, I guess we could use log cosines, but we would have to find this side first because you have side, angle, side. So you could use log cosines to find that side. And then you could use log cosines with side, side, side to find angle. But that's a lot harder than it needs to be. Right, so right triangle, just do what you did last semester, or even in geometry. You know the opposite and the adjacent. So that's tangent. You're finding an angle, and you're inputting a ratio, so inverse tangent. Tangent's always opposite over adjacent. And that's not something that we're going to know, so we would have to ask our calculator to do that for us. We would be in radian, degrees. It's not to 3 decimal places. Just right triangles, so inverse over pillar is fine. I mean, by all means, do log cosines if you want to, but you're going to have to do 2 parts of log cosine. That's more work than is necessary. But it should be. Alright, now that we've got the 2 things we want, this is no better than step 1 on the other page. The vector will be the magnitude out front, times parentheses, cosine of the angle, determines the horizontal component, plus sine of the angle, always the same angle, J, so that determines the vertical component. And instead of writing it well, in that case, I said we will. So this one, I want you to try, but again, I just want you to be one step ahead of me. But I do want you to try before I do this the same thing. If you got this, so you should be able to sketch a picture of it pretty quick. So sketch a picture, let's make sure our pictures are the same, and then you can try the next step. So your picture should start somewhere, and it should be going left 5 for up 2. It's kind of like a slope. It's telling you how fast it's going up for how much time. It also is passing direction over. Okay, so if your trigonometric form gives magnitude and the directional angle, see what you would do to find the magnitude of that, and see what you would do to find the directional angle. So try this next. 100% necessary. I think you should appreciate a little bit more here. You probably don't need a picture to visualize what your area here is going to look like. Leg squared plus leg squared is hypotenuse squared. So the hypotenuse of the length squared is 29. That's what we're going to call that our magnitude. We're good there. Okay. You want to find this angle. You've got a right triangle, and you know opposite and adjacent. And for these type of questions, you're always going to know opposite and adjacent because you're being told the vertical component and the horizontal component. Going to always be inverse tangent for these. Opposite over adjacent. If you want to type it in your calculator, trust our calculator, negative 21.801. So that's the directional angle you got. What quadrant is negative 21 degrees in? Is this guy going down in quadrant 4? So then that's not the angle we want. So what do we have to do with that last semester? Practical one, add one in. So the reason why you have to do this sometimes is because remember inverse tangent. Remember, all the inverse functions have those ranges we have to memorize. So when you ask your calculator this, you're saying, find me an angle that has a tangent of negative 2/5. And it does that for you. It says it's right here. And it gives you an angle within that range. So we can't list them all out. There's infinitely many. But from our picture, we can see we don't want this angle down here. We want this angle over there. So when it was incorrect, you don't always do this. But when it was incorrect, you need to add half of that. Or I guess add one in. Because this is degrees, so keep our units consistent. But the real angle is 158.19 degrees. So obviously I want you to understand why your calculator is wrong here. I think that's good for you. I would hope that you just remember that from last semester. Worst case, if you've got the picture in front of you, if the angle that the calculator gives you makes sense, then don't add 180. 56 degrees, this looks like 56 degrees. I didn't add 180. But if it looks like it's in the wrong direction, it looks like it's pointing opposite, then you need to add 180. Now you've got what you need, so see if you can piece those two things together before triggering the measure. And if you're familiar with that form, it's really just putting those puzzle pieces together. Magnitude out front, parentheses, cosine of this angle, the horizontal component, plus sine of the same angle for the vertical component. So, you like both forms. I can glance at this and tell you the magnitude and which angle it's heading at. And I like this form because I can glance at it and tell you that it's going left 5 or up 2. They just have different angles. It's not that I can't figure out the directional angle and magnitude from this, it's just that it takes me a little bit of work. It's not that I can't figure out how much this is going left and right, left or right, and how much up or down. It just takes me a few steps. Questions you guys want to ask? Switching back and forth between the forms. Question 33 through 33. It's 433. Any of those? Alright, so now we can start to piece some of this together and actually do a real-world type of problem where you can see why you might care to be able to do all this stuff. Why do we need the main magnitude? Why do we need component form? All that. Alright, so what if we had multiple vectors? So if we had multiple forces and we represented them each with their own vector, and we break them into component form, it's easy to see overall what's happening, so the result of that. So, question that we're going to be working on is whole vector page, so we don't normally need this much space, but just to space it out, have a bunch of notes. Imagine an airplane heads at a 30-degree bearing, and it is heading at 400 miles per hour. So, this is one vector. So, 30-degree bearing, remember if it doesn't give you directions, you should assume from the north line, measure clockwise. So I'm going to say I'm starting here. Switch the vector. So from the north line, and is it bearing at 30 degrees? So try to turn 30 degrees. Make sure you label that as 30. And then that's the direction he's heading. And he's going at 400 miles per hour. So I guess that's great in a vacuum. There's no resistance, no air resistance, but that's not really how things work in the real world. So we also have, I'm going to highlight all of this, 400 miles per hour, and that bearing is that way. Okay, but we also have some wind involved. And the wind is blowing southwest at 15 miles per hour. So what you really want to do, and there's two ways you can sketch this, but the way I think is most useful for people to see is start your second vector at the end of the first vector. So imagine this like another set of xy. Okay, if it's blowing southwest, so it doesn't give me an angle, so that would mean it's exactly in the middle of southwest. Here's south, here's west. So it's going right here, right in the middle of that quadrant. So this little guy right here would be 45 degrees. And it's blowing at 15 miles per hour. This so our plane would be going this fast at that angle, but we've got some wind in this question, and it looks like the wind's in our face, so we can visually see that it's slowing us down, and it's pulling us down a little bit. So there needs to be a third vector in here, and the third vector is called the resultant vector. The third vector is the result of the first two forces. So that's where it gets its name, resultant vector. So you're going to start at the first vector, and you're going to say, okay, if there was no wind, I would do this, but I do have some wind, and it's going at this angle and at speed. And obviously, the more the scale this is, the more it makes sense. 400 miles per hour should be much stronger than 15 miles per hour. If I would be doing this, but I've got this pulling me this way, then this would represent my resultant vector. That's the result of the airplane and the wind. Starts with the first vector, ends at the end of the second vector. Now, I hope that kind of makes sense to you, because I can see the airplane is going right and up, and I can see the wind is dragging it left and down. So the result of both of those things happening would still be going right and up, but a little bit less than what the airplane would do with no wind. So there's the visual of what's going on. Now, for us to actually compute what's going on with this resultant vector, because I want to know what speed is the plane actually going at. In other words, how much is that wind actually slowing it down? And what angle sometimes is it actually taking with the wind pushing it that direction? It's not as hard as it seems like it would be. So what we want to do is we want to think of each of these vectors in component form. So I want to just know that the airplane goes right up. I want to know how much right and how much up. Okay, well, what's the magnitude of the airplane? 100. Okay, so that's what I need for trigonometric form. What angle is it making? I heard 60 and 30. Those would be the two most common answers. 30 is the bearing. If I'm plugging an angle into sine and cosine, it assumes I'm starting from positive x-axis. So it might be 30 from north on clockwise, which is bearing. But when I plug a number in here, it wants to know how much from the positive x-axis do we go in that direction, like we did in trig. So it's not 30, it's 60. And I will say that's probably going to be the hardest thing for you on these question types. So I'll try to emphasize it for you to help out there. That you're plugging an angle in the sine and cosine is the angle from the positive x-axis. Almost never the same thing as the bearing. Okay, so I could switch this over. I prefer to look at it like this. So 400 times the cosine of 60. And the cosine of 60 is what? Okay, so 400 times a half would be 200. And then if I distributed this sine of 60, it would be square root of 3 over 2. So this would be 200 square root of 3. We reduce that. So what this represents is going 200 miles per hour to the right and 200 times the square root of 3 up. I just looked at that one vector so far. Okay, now let's do the same thing for the second vector. By the way, you could have as many vectors as you wanted to. You could have 8 different forces, and this logic would still work. You want to have something. So the wind, what is its magnitude? Okay. Cosine of some angle I plus the sine of the same angle j. Now, they didn't give me a bearing, so I think you're more likely to slow down and think about this one. If I'm about to plug an angle in the sine and cosine, and I just warned you this is where most mistakes will occur. You gotta be careful. It's from the positive x-axis. So from the positive x-axis, what is that angle? Like 180 plus directly in the middle of this quadrant, it could be another 45. So it would be 225. Always the angle from the positive x-axis. It's not that you have to do a bunch of work to find it easily, it's just that you need to be looking from the right way. When I plug this in my calculator at some point, or I will press a unit circle at some point, 45 means it's going right and up. 225 means it's going left and down. It would have a completely wrong signs. So the wind would be 15 times the cosine of 225, and the cosine of 225 is negative square root of 2 over 2. We're just multiplying these and using the unit circle. The sine of 225 is also negative square root of 2 over 2, so 15 times that. Think about what these numbers mean, because this is where it's going to all come together. This component form of the airplane is telling me how fast it's going to the right and how fast it's going up. The component form of the wind is telling me how fast it's going to the left and how fast it's going down. So if I want to combine those two things together, we can combine them together with adding, because both of those forces are happening. So I can say, take this vector, and also factor in this vector. And when we add those together, what I'm going to get is I'm going to get the component form of the resultant vector. So I know my picture's a little messy here, but the resultant vector is going to be this. So I'm going to actually know how fast it's going to the right and how fast it's going up when we add these together. Okay, so I'm going to squeeze in a step here. To add vectors together, we just add the vertical components together with the vertical component, the horizontal components together, with the horizontal component. And so that's a great exact answer. I know that it means a lot to us until we type in our calculator and look at the decimal. What kind of number should we expect? What do you expect this to come out to be? What here? More than 400? And it should be a little bit less than 200, right? Because the wind is in our face, so it's slowing us down. We're not going quite as fast to the right. So, it's like going 200 miles per hour to the right. I'm doing about 189 miles to the right. And instead of doing 200 square root of 3 north or up, the wind was in our face, so it's slowing us down a bit. And it's not just, we can see that it's slowing us down a bit, we're measuring how much it's slowing us down. So I can ask my calculator, 200 square root of 3 minus 15 square root of 2 over 2. And so it was doing, I guess I don't know what it's 335.83 approximately. And since that's the resultant vector, that's the result of both vectors. Now I know how fast it's going to the right and how fast it's going up. This is in speed. Okay. And then usually the question that we want, now that we have this information, I'm going to store this stuff in my calculator as A. Store this stuff in my calculator as B. So we can get this. Actually, let's do S. I think solutions are want to do this. Okay, so this is what my calculator knows as X. This is what my calculator knows as Y. Let's store those two. Okay, so no one, I don't know, you ride an airplane or you work for an airplane company or whatever. This flight, they don't, I don't know many instances where you care how fast you're going east and how fast you're going north. I mean, it's kind of nice to know, I guess. But what you really care about is how fast is your plane going. How fast your plane going will be the magnitude of this. And if we have the component form, that's what we get on the front page of our notes. The component form is to be like X and Y. I'm just trying to find the hypotenuse of the right triangle. So the hypotenuse will be the square root of the leg squared plus the other leg squared. I'm calling them X and Y because this I stored it in the front. And because it makes it really easy to type in. And this number makes sense to me. The plane said it was doing 400 miles per hour. The wind was in its face, so it's slowing it down. It's like it's slowing it down about 15 miles per hour. And I know what bearing it was taking when it started. but the wind is pushing it a bit, so unless we correct it, we're not going in a very declared wind anymore. So we can find this directional angle. Again, if you understand what these are, it's a leg and a leg of the resultant vector. A leg and a leg of the resultant vector. It's like you can tune all the rest of this stuff out. If you want to know the directional angle when you know opposite and adjacent, you can do inverse tangent of opposite of adjacent, and maybe add one equal, depending on what quadrant it's in. This is in quadrant 4, so I'll go ahead. So it was going at a directional angle of 60, but the wind pushing it that strong at that angle actually makes it go at an angle of 60.575. Very close to the same, obviously not exactly the same, it's making a difference. Now again, we only do 2 vectors at a time, so it really amounts to, can you break this vector into component form? Can you break this vector into component form? You want to figure out what the result is, add them together, then you've got the resultant vector, and if you've got the component form of the resultant vector, that into m to the function magnitude, or in this case, angle, and then you know what the result of both of those vectors are. And you should have a career in science, and you're going to take into wind, resistance, 7 other things. You could just do 7 vectors, and you have to get all 7 vectors in the component form, but you can add all of those up, get the component form of the resultant vector, and then you can figure out what the result is in the magnitude or angle. Exactly the same way it would be more tedious adding 7 vectors together and getting 7 component forms, but the logic is still hold. So what I want us to do is keep that out. If we look at the worksheet you picked up today, so the front page is just some general stuff. It's not really word questions. Given a point, can you find the component form and the magnitude? Given a couple vectors, you know how to do that arithmetic that goes along with it. You know what a unit vector is and how to find it. Do you know how to find the directional angle of the vector? Do you know how to find a vector that has this magnitude in the same direction as that vector? All this is sounding familiar to me. Can you find the component form of the vector that has that magnitude at that angle? And then like the last page of our notes, if you had 2 forces, one's pulling this strong at that angle, and this one's that strong at that angle, if we could get both those vectors into component forms, add them together, we can figure out what the direction and magnitude is of the resultant vector. And then exactly the same thing, just hairpinning. So to me, I would say questions 1 through 5 are more just a process. So I would like you to try all the questions 1 through 5 first. Once you finish questions 1 through 5, go ahead and move on. But once I think you've had enough time, we will go over all of those 1 through 5, and then I'll give you more time to try the others. We'll be over this. Not sure about something, skip it, just start by it, and if you finish the other 5, then use your notes and go back to it.